Okay, so here in this video we will discuss various numericals of multiplexer. Various numericals of multiplexer. Okay, now any mux can be designed using two different approaches. First one is known as expansion approach, and the second one is known as compression approach. Okay, so when we follow expansion approach, first we will discuss about expansion approach. Expansion approach. When given mux is having less inputs and required mux and required mux is of higher inputs. Okay, when the given mux is having less inputs and the required mux is having a high output input, at that time we will use this expansion approach. For example, if I want to design 4x1 mux using, if I want to design 4x1 mux using 2x1 mux. So which mux is given? 2x1 mux is given, and which one is required? 4x1 is required. Okay, so here you can see this 2 is less as compared to this 4. Okay, so here for designing we will use expansion approach. Okay, so how we deal with this type of example? Okay, in this type of example we will check how in given encoder how many inputs are there. Suppose here 2 inputs are there, and in required multiplexer how many inputs are there? There are 5 inputs. So how much time we add the inputs of given encoder for completion of required encoder input? So when we add 2 2 times, when we add 2 times, so we will get 4. It means that we need 2 2x1 mux for the designing of 4x1 mux. Is it clear to all of you? Now, how can we design? How can we design? Step number 1. How can we design? Step number 1. In required in required mux, input equals input 2 raised to power n equals to 4. Small n will be 2. Okay, now its truth table will be A and B. These are the selection lines and this one is the output. When 0 0 0 1 1 0 1 1, this one is the truth table for 4x1 mux, and this one is the block diagram of 4x1 mux. In 4x1 mux there are 4 inputs. I am representing these inputs as I0, I1, I2 and I3. And to select these and to select one inputs from these four inputs, we need two selection lines. So here I am representing selection line as AB. Okay, accordingly we will get output. So here, because we are taking selection line as AB, that's why here in the truth table I am considering AB as an input. Okay, so when AB equals to 0, at that time this I0 will be transmitted towards the output. So when AB equals to 0, then we will get output as I0. In the second case, we will get output as I1. In the third case, we will get output as I2. And in the fourth case, we will get output as I3. Is it clear to all of you? Okay, now step number 2. Step number 2. Given encoder, given mux is having inputs 2 raised to power n equals to 2, so n will be 1. Okay, now step number 3. Final design. Step number 3, final design. We know that we have 2 cross 1 mux. Okay, so we will take 2 cross 1 mux. 2 cross 1 mux. This one is 2 cross 1 mux. Okay, these are the inputs of 2 cross 1 mux, and this one is the output of 2 cross 1 mux. Now we need to design 4 cross 1 mux. That's why we will take 2 cross 1 mux. 2 cross 1 mux. Okay, this one is I0, this one is I1. Here two inputs are there, I0 and I1. If we till we not connecting these multiplexer, at that time we represent these inputs of second encoder as I0 and I1. But when we connect the selection line of first encoder with the selection line of second encoder, at that time we will take these inputs, we will take the first input of second multiplexer after the last input of first multiplexer. It means that these are the selection lines. It means that if till we have not connected, so here I am writing I0 and I1 because I have not connected any upper multiplexer with the lower multiplexer. Okay, now here we will see this one, these multiplexer contain a single selection line. Okay, so but in 4 cross 1 mux we need two selection line A and B. Okay, so what we will do, we will represent this selection line as B. We will take this selection line as B and also take it as common. Okay, we will take this selection line as B and connect these both selection lines. Okay, so this one is the common selection line in this. Okay, now here if we connect these selection line, so at that time we will write these input as I2 because the last input of first encoder is I1, so here I am writing I2 and this one is our I3. This one is our I3. Okay, now in this multiplexer design we have two outputs, four inputs. We have two outputs, four inputs, but two inputs, four output, but only single selection line. But in 4 cross 1 word, we need, in 4 cross 1 mux we need two selection lines. Okay, so that we will take one more 2 cross 1 mux here. We will take one more 2 cross 1 mux here. Okay, so here the inputs are, here the inputs are 0 0. Here instead of these 2 cross 1 mux, here instead of these 2 cross 1 mux, here instead of these 2 cross 1 mux, we can use a simple AND gate, a simple NOT gate. Here I am taking a input A, and by using a NOT gate, I am connecting it in the enable port of first multiplexer. This one is nothing but a enable port. You can assume it as a supply. Okay, now now we will connect we will connect we will connect okay, we will connect next into second multiplexer. Now what happened? Now what happened? There are two selection lines. A and B will act as a selection line. Four inputs are there, but here there are two outputs. So to find out one output, I will take one OR gate here. I will take one OR gate here. This OR gate will provide me output O. Now how it works? We know that when A and B equals to 0 0, at that time O will be I naught. Now look how it works. When A equals to 0, when A equals to 0, when A equals to 0, so because of this NOT gate, here we will get 1 and here we will get 0. Okay, so here we will get 1, so it will enable the upper multiplexer, but the below multiplexer get enable pin as 0. That's why it will not activated. Only the upper one will activated because of this A. Okay, now B equals to 0. Now when B equals to 0, so at that time this input in the 0th pin, that is I0, will be transmitted here. So what we will get here? Here we will get I naught, and here because it is not activated, we will get output as here we will get input as 0. So what we will get the output of this OR gate? We will get output of this OR gate as I naught plus 0. It means that we will get output as I0. Okay, now when we consider our second case, when A equals to 0 and B equals to 1, so according to truth table, we have to find out, we will find output as I1. So let's see what happened when we take I equals to 0. When we take I equals to 0, so similarly the output of NOT gate will be 1. It activated the upper multiplexer, but because of this 0, the below multiplexer will deactivated again. Now B equals to 1. Because of this B equals to 1, this I1 will be transmitted here. Okay, this I1 will be transmitted here. So in the second case, what we will get in the output? We will get output as I1 plus 0. So the output will be 0 in the second case. Okay, now what happened in the third case? When A equals to 1 and B equals to 0, when A equals to 1, when this A equals to 1, so because of this NOT gate, this will be 0 and the below one will be 1. So when this one will be 0, so it deactivate the upper and multiplexer, but it activate the lower multiplexer. Okay, now when B equals to 0, so when B equals to 0, so it will activate this I2, it will activate this I2, and this I2 will transmit it towards this side. So here what we will get here? Here we will get I2, and from the upper we will get 0. So what is the output in the third case? In the third case, output will be 0 plus I2. So the output will be O equals to I2. O equals to I2. Okay, and the last case, when both inputs are 1 1, when both inputs are 1 1, so similarly the upper one will be deactivated and the lower will be activated. B equals to 1, when B equals to 1, so this I3 will be transmitted from the lower path through here. So here we will get I3. So what we will get? We will get O equals to 0 plus I3. It means that O equals to I3. Okay, so this one is our first design. This one is the first design. This one is our first design in which we implemented 4 cross 1 mux using 2 cross 1 mux. Okay, now second, if second question, if I want to design 16 cross 1 mux, if I want to design 16 cross 1 mux using 4 cross 1 mux, or suppose 8 cross 1 mux. If I want to design 16 cross 1 mux using 8 cross 1 mux, so using the previous approach, how much multiplexer we need? How much multiplexer we need? 8 plus 8 equals to 16. So how much multiplexer we need? We need two multiplexer having 8 inputs. Okay, so here I am taking a multiplexer having 8 inputs. Here I am taking a multiplexer having a 8 inputs. Is it clear? This one is having one output, this one is having one output. Total 8 inputs are there, I0 to I7. Similar, I0 to I7 till we not connecting the selection lines. Okay, now truth table of 16 cross 1 mux. In truth table of 16 cross 1 mux, suppose I am taking selection line as S3, S2, S1 and S0, and accordingly the output will be 0. If the truth table of 16 cross 1 mux is like that, and when the selection line when the selection line value is 0, so we will get output as I0. When the selection line value is 0 0 1, so we will get output as I1. we will get output as we will get output as I1. Similar for the other condition. At last, for last output combination, last selection line combination, we will get output as I15. Okay, so here for the designing, we this S0 and S1 are the LSB as compared to S3 and S2. So that's why we will take these LSB as the selection line for these 8 cross 1 mux. Okay, so what is the selection line here? This selection line will be S0, S1 and S2. Similarly here, the selection lines are S0, S1, S2, because we now here I am taking the selection line as common element. That's why the input will be I8 to I15. Is it clear to all of you? Now here there are 3 selection lines, but we need one more selection line also. We need one more selection line. Okay, so for one more selection line, we will take S3. We will take S3 and now connect this S3 with a NOT gate, and similar similar from the previous question, we will take its output as an enable element of the first encoder, and same as we will take we will take the we will take the out we will take the S3 as a enable pair for the second encoder, second multiplexer. Okay, so when s equals to 0, so upper one will be activated and we will get the output from this input, from this multiplexer. And when when s3 equals to 1, at that time we will get the output of NOT gate as 0, so it will deactivate the upper multiplexer and will activate the below multiplexer. Okay, now here we are having two outputs, so we can connect one, no, we can connect OR gate and this will provide us output 0. Okay, so this one is our second question. Now our third question. Here we have to design 16 cross 1 mux. Here we have to design 16 cross 1 mux. This one is the required. Okay, here we have to design 16 cross 1 mux using 2 cross 1 mux. So how many 2 cross 1 is required? How many 2 cross 1 is required? 2 plus 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 2. How many 2's are required? 8 2's are required to complete this 16. It means that total 8 to in starting 8 2 cross 1 is required in the starting stage. Okay, now first we will make a truth table for this 16 cross 1 marks. Here I am considering a selection line as ABCD. Here I am considering selection line as ABCD. Okay, and the output as O. Output as O. This one is the truth table for this one is the truth table for 16 cross 1 marks. Now what is the block diagram of 16 cross 1 mark? This one is the block diagram for 16 cross 1 marks. This one is the block diagram for 16 cross 1 mark. Here the input is I0. Here the input is I0, I1, I2 till I15. And because there are 16 inputs, so to select these 16 input we need 4 selection lines. These are our selection lines, that is A, B, C and D. Accordingly we will get output as O. Okay, so this one will be the block diagram and this one is the truth table. So when we put ABCD equals to 0, when we put ABCD equals to 0, at the time we will get output as I0. When we will put 0 0 0 1, so we will get output as I1. Similarly, when we put input as 0 0 1 0, so we will get output as I2. Similar for the other combination also. And when we put the last combination 1 1 1 1, so at that time we will get output as I15. Okay, now we will design. Now we will design. Now design. How many 2 cross 1s are required in the starting? How many 2 cross 1s are required in the starting? Total 8 2 cross 1s are required. Total 8 2 cross 1s are required. So this one is our first 2 cross 1. This one is the second 2 cross 1. This one is the third 2 cross 1. Third 2 cross 1. This one is the fourth 2 cross 1. Fifth 2 cross 1. Sixth 2 cross 1. Sixth 2 cross 1. Seventh 2 cross 1. And eighth 2 cross 1. And eighth 2 cross 1. These are the 2 cross 1 multiplexer. Now the inputs are I0, I1, same as for the other one also, same as for the next one, and it will repeats. Okay, now from this end we will get how many outputs we will get from here. We will get how many outputs we will get? We will get total 8 outputs because total 8 2 cross 1 mux is there. So we will get total 8 outputs, but in 16 cross 1 only one output is there. So here again we need, so here again we need 2 cross 1 mux. Here again we need 2 cross 1 mux. Here again we need 2 cross 1 mux. And at last we again need 2 cross 1 mux. How many outputs are there? Now there are 4 outputs. So again we need one more 2 cross 1 mux. From this end again we need a 2 cross 1 mux. Now it will provide here. Now it will provide here. So here we will get 2 cross 1 mux, and from this we will get the output. So overall there are 1 2 3 4 overall 16 inputs are there and one output is there. Okay, now This one is the, now we will divide it into stages. Now we will divide this diagram into stages. Now we will divide these diagram into stages. Okay, so here this one is our first stage, this one is the second stage, this one is the third stage, and this one is the fourth stage. Okay, this one is our first stage, this one is second stage, this one is third stage, and the last one is this one is our fourth stage. Okay, so the multiplexer that provide the output is always the multiplexer that provide the output always contain a selection line that is LSB. It means that it means that here it means that it means that in truth table this D is the LSB and this A is the MSB. So the multiplexer that is close to the output will contain a selection line LSB. Okay, now here here the second stage multiplexer will contain the neighbor of LSB, that means it will contain the selection line as C. Now here these multiplexer contain selection line as B. These all will contain selection line as B. And at last the first one contain a selection line A. All of them contain a selection line A. All of them contain selection line A. All of them contain selection line A. All of them contain selection line A. Because the selection line is common, that's why we will take now input as I2, I3, I4, I5 till I15. Till I15. Okay, so this one is the designing, this one is the designing of 16 cross 1, this one is the designing of 16 cross 1 mux. Here you can see there are 16 inputs, total 4 selection lines and 1 output. So this one is the 16 cross 1 mux by using 2 cross 1 mux. Okay, thank you so much.